Awesome.
Good morning, everyone. This is Dr. Richard McCreery. He is a professor of chemistry at the University of Alberta. And he'll be telling us a bit more about what he does with chemistry just in a bit. But first, I'd like to say hello to all our camps joining us across Ontario, from Sudbury to Windsor. We have you watching this live, and I see lots of great questions already coming in on Twitter, so I'm really excited to get to those in a minute. As you know, today is Chemistry Day. Campers will be doing a few different chemistry experiments and activities today, including watching gobstopper candies dissolved in water, learning about non-Newtonian fluids, making a super bouncy ball, and a crystal snowflake through chemistry. So before we get to the campers' questions that might help them with these experiments and challenges, Dr. McCreery, can you tell us a bit more about what you do with chemistry?
Sure. We try to use molecules as electronic circuit components. So we put molecules into circuits, and circuits could be computers, could be music, could be memory devices, that sort of thing. Now, I did send some slides. Can you show those?
Yes, I can.
These slides, just a couple of them, show the general idea. And the first one is the general term is molecular electronics. And you can see that in the center is a device called a molecular junction, where we connect some molecules between two conductors, in this case carbon and copper. And the V over on the left represents a voltage, so that's a circuit, just like happens in your flashlight or your computer. So the question is, what can molecules do as elements in circuits? I mean, we have this wide world of silicon that does all these amazing things. Molecules are different, and I show a couple of pictures of what these things look like. And in the upper left is a wafer made of these molecular junctions. So molecules are electronic systems. They have electrons running around in them. So this is a particular molecule, complicated name of nitroazobenzene, and it is the little blobs you see in the bottom are electrons going around the atoms. So you have electrons moving in atoms. So why not use it for electronics? And the big question is in molecular electronics is how do molecules behave in a circuit? You know, how do you hook them up? What do you use for your alligator clips? That sort of thing. And secondly, if you figure that out, what are you going to do with it? What can you do that's any better or different from what you're already doing in widely with silicon? So I have an application, and it's on the next slide. And assuming that we can get this to work, and there's lots of interest in it, this will be the world's first commercial application of molecular electronics. So you take a guitar output, and guitarists normally go through things called overdrive pedals. These process the guitar sound before it goes to the amplifier. And these are incredibly common. There are millions of these sold every year. And every electric guitarist knows about them, and every electric guitarist has probably got 5 or 6 of them. And we have a company in town that happens to be called Dr. Scientist Sounds in Edmonton, and he makes these things and sells about 100 a month. So one of my coworkers, Adam Bergman, is interested in guitars, and so he said, what if we take our molecular devices and put them into a guitar pedal? So we did that, and so when you hear some music in a few minutes, the music will go through the molecules, and it'll be changed. It's not an obvious change. You can hear it, but it's not a great change. What it's actually doing is changing the so-called harmonic content of the music. by creating intentional distortion. And molecules do this differently from anything you can do with silicon. So the box in the lower middle is one box that this Dr. Scientist, his name is Ryan Clark. He sells these things, and he sold about 1,000 of this particular unit. And if you look, you can see it closely. On the bottom of that little white box is a button. And that button is what the guitarist will push when he wants to get the special effect. And on the right is the internal circuitry of that box. And what we did was to take our molecular device and modify the box. It's actually a different one that I'll show you in a sec. And they use that as our test. And so you're gonna if you look at the next slide, we're going to show this is the upper part of the picture is a guitar amplifier. You've probably seen these before. It's an amplifier and speakers. The little yellow box in the bottom is the so-called distortion pedal. And you can't see it in this picture, but on the side of that box is one of our molecular devices. So you're going to hear about 10 seconds of just Adam playing a few notes and chords on the guitar. And then if you look closely in the lower right, there's his foot. And you're going to see his foot pushing down on the pedal. And then in the upper part of the little yellow box is a little red light. And when that red light comes on, the music is actually going through the molecules. So just imagine that for a minute. Imagine these molecules with all these electrons in them. And of course, molecules are held together by electrons. As I say, they're inherently electronic devices. And imagine that this guitar, the cable on the left of the yellow box is the guitar input, and then on the right is the output, and the output goes to the speaker. So imagine that while it's in that yellow box, it's actually going through these molecules, and try to listen for the difference after he pushes the pedal. So you hear about 10 seconds with just simple guitar music, and then about 10 seconds with the molecular device, and then it'll go off again just so you can compare them. So assuming this all works, please go ahead.
Okay.
You can turn it down a little bit. Well, I don't know how that was at your end, but it was somewhat broken up on this end, so it didn't translate all that well across the web. But anyway, there it is. So that's the near term. Is we want to make devices that have molecules in them, and the guitar will be the first one. So I'm happy to answer questions.
Yeah, no, that's awesome. Some really cool science there. Molecular music, I guess. That's a really groundbreaking idea. So I'll get right to the questions from some of our campers who want to know more about chemistry. There's one here from Brantford. Shout out to Brantford this morning. They want to know, how can you make chemicals explode?
An explosion. The funny thing is that when you ask chemists why they're chemists, they'll usually give you one of two answers. One is that they like to make neat colors change in solution, and the other is they like to blow things up. So an explosion is just a chemical reaction which generates a lot of energy, but it generates it very quickly. So imagine a fire burning in your fireplace. That's releasing a lot of energy, but it's doing it slowly. If you packed an hour worth of fire into a thousandth of a second, then it would be pretty exciting. So it's rapid generation of energy, and what you look for in an explosive is something that's got a lot of energy in it, and something that reacts rapidly. So things like TNT, trinitrotoluene, is something where you have an oxidation by the nitro groups of the benzene ring, and that happens very quickly. So it's just a fast chemical reaction. That's it.
I see. So the faster the reaction, the bigger the explosion.
Yeah.
Brantford had another question going back to chemistry and colors. They wanted to know, can chemicals change color? And I guess I would ask, how can you make chemicals change color?
Well, color is because most of the light around you is white, either sunlight or from the room lights. And so white light contains all colors, as you probably know. And Isaac Newton was the first one to figure this out. And so it has blue and red and green, etc., but it's all mixed together and it's white. Well, now if you have a molecule which happens to absorb one of those colors, say red, then you hold that up to the light and you're going to see that the red is going to get absorbed by the molecule. And what it's doing is another form of energy transfer. The energy is being absorbed from the light and going into the molecule, and it's actually going to heat up the solution just a very little bit. Now what's left, of course, of the white light is now anything except red, which is going to be blue and green. So that a molecule absorbed red light will appear to be yellow and green. And the reason why different molecules absorb different colors is because of the way that their energy levels line up, and those little blobs of electrons you saw in the second slide. Those are what is involved in moving those electrons around. Is what happens when a molecule absorbs light, taking it from one place in the molecule to another. So it's different colors, and the way you change colors is by changing molecular structure in some way, so that it goes from being a blue absorber to a red absorber.
Okay. Here's another good question. This one from St. Thomas. Good morning, St. Thomas. Thanks for your question. They want to know, what is the most dangerous chemical?
The most what?
The most dangerous chemical.
Dangerous chemical. Well, I guess that depends on what type of danger would you like. Yes, some molecules are more reactive than others. Favorites on there is probably be nitroglycerin, because it's not only very reactive, but also very unstable. But then there are also danger in the form of toxicity. There are certain mercury derivatives which are deadly at very tiny amounts. I mean, millionths of a gram of methylmercury is bad for you. So that's a case of chemical toxicity. And then I guess a third way would be corrosion, reactivity. Sulfuric acid, sodium hydroxide, which is Drano. Those things are very, very reactive. They don't blow up, but they corrode things, so they cause damage to skin and to materials in your kitchen or whatever. So, you have to remember that everything is made out of chemicals. There's no way around that. Chemistry is everywhere, and chemicals that we use in the lab are refined and purified, and sometimes they're concentrated, and those can be fairly dangerous. Yes, so there's a whole lot of safety issues that go on in a research lab, and everybody has to know about those things. So I guess there isn't any most dangerous chemical. Most chemicals are not particularly dangerous, but of course some of them are, and some of them certainly deserve respect. And I was speaking as a practicing chemist for 40 years. Heavy metals worry me, but none of that worries me as much as biology, right? Because in biology, like viruses and that sort of thing, they can reproduce. Chemicals don't reproduce. So they need to be treated with respect. And yes, you need to know what you're doing. But, sugar is a chemical, so it's just a wide range.
I see. So a word of warning for biologists. Thanks for that
Word is
answer.
what?
A word of
I
warning for biology and biologists.
Oh, yeah, yeah. Well, nothing against biologists, just Mother Nature, is there are dangerous things in Mother Nature.
Yeah. So I'll go to
Mm.
our next question from our camp in Paris. Good morning, Paris. Thanks for your question. They want to know, are gooey things a liquid or a solid?
Gooey things?
Yeah, and they might be
Is that what you
talking
said?
about, yes, yeah.
Well, it's like many things in science. We have these words, gas, liquid, and solid, but then there are things that are somewhere in between. So take one gooey liquid I think of is slime. All right, slime is a big molecule called polyvinyl alcohol, and it's got in it a small amount of a different molecule. It's a sodium borate, which causes those big polymers to be to attract each other. So if you took the active ingredient of slime, the polyvinyl alcohol, it would be a solid. But the solid dissolves in a liquid in water to make this kind of thick liquid, and then the borate makes it thicker. So you have a range between a pure liquid, which the range, the word you're looking for here is viscosity. If you have a material which has a very low viscosity, like water, then we always call that a liquid. And there are organic things which are even less like that. But as it gets more viscous, like you get to maple syrup and then peanut butter, then you're talking about things that are much thicker and don't flow as easily. So there's a wide range between liquid and solid, and I would say that rather than just having an A and B statement like black and white, talk about viscosity. Viscosity is a range, and things can go all the way from thin liquids to hard rocks, depending upon their viscosity.
All right. So I guess I was wondering, they're working with non-Newtonian fluids. So is that just a liquid with a high viscosity, or how is that different?
Well, I'm not an expert on non-Newtonian liquids. It's and I'm not sure that I like the term. But what they're trying to describe is that when you have a material which doesn't react the same way as Newton says, you push on it and it pushes back and it changes. So I would say that a non-Newtonian liquid is a viscous liquid, yes, and it has a whole lot of hydrogen bonding in it. The way that these things work, both slime and non-Newtonian liquids, is by hydrogen bonding. And hydrogen bonding is very important. It's what makes water behave the way it does. It's the interaction between a hydrogen atom, a proton, and usually oxygen. And so hydrogen bonding keeps water together. So water is a liquid because of hydrogen bonding rather than a gas. So a non-Newtonian liquid is just a description of, at least my understanding, it's just a description of something that it doesn't behave like a normal liquid. So most of the ones I've seen I would consider viscous liquids. But again, black and white may not apply well here. Liquid and solid are simple terms, but there's lots of things in between.
Okay, thank you for your answer. I'll go to the next question from our camp in Sudbury. Thank you, Sudbury. What happens to the molecules when you mix something hot with something cold?
When you mix something hot and cold,
Yeah,
or
what
make
happens to
something,
when you mix?
well,
Uh,
yeah. Nothing. Well, if you just take hot and cold water, the, the there's various ways you can have energy in a molecule, and every molecule's got energy in it to start with. And when you have water molecules, they're all the same shape, they're all the same size, and when you mix them together, hot or cold, they're still water molecules. The difference is that in hot water, those molecules are moving around a lot. They have kinetic energy, and or thermal energy. They're also vibrating. You got atoms in there which are bonded to each other, and they can vibrate against each other, just like two balls attached to a spring. And that's called vibrational energy. And if you go from cold to hot, or say from ice, the extreme, where the molecules are moving very little, and you go all the way up to steam, then you have a wide range of energy. So if you take hot water, you've got vibrational energy and kinetic energy, thermal energy. All those things are high, whereas in the cold water, they're low. And when you mix them together, the molecules themselves don't change, but this energy gets distributed among all the molecules in a mixture. So some of the vibrating ones slow down, and some of the ones that weren't vibrating start vibrating. So you just kind of homogenize the energy through the liquid. So nothing happens to the molecules themselves in that case. All you're doing is changing the amount of energy in each molecule.
Okay. So our next question from Ingersoll, shout out to Ingersoll. They want to know, what's the difference between a physical and a chemical reaction?
Well, most people define a chemical reaction as one where you have a bond being made or broken. So you take water again. You got two hydrogens bonded to an oxygen. And the bond is the electrons that are between the two that hold them together, just like the structure you saw. Okay, well, a chemical reaction means that one of those bonds breaks. In the case of water, it could be so-called dissociation, and H2O can become H plus, a so-called hydrogen ion, and hydroxide minus, which is OH minus. Hydroxide minus being the active ingredient of Drano. And so that's a chemical reaction. Physical reactions, people more talk about them as where the bonds are not changing. It's still the same molecule. So your mixture of water and hot and cold water, I would call that a physical process, and you're not making and breaking bonds. And so, but again, that's another case of where yes, everybody knows that we have physics and we have chemistry, but there's some ground in between. And what we do, I joke that sometimes I get accused of being a physicist because we work on things that look like physics. So I think making and breaking a bond is certainly a clear distinction, yes. But I'm not sure but there's a range of things between those two. Like everything has shades of gray.
Yeah, very interesting the way everything can be connected like that. All the different sciences, physics, chemistry are somehow connected. So that's all the time we have for today's call. I'm really sorry that I couldn't get to more questions from all the camps. There's some great questions coming in on Twitter. So hopefully, maybe Dr. McCreery, I could email you some of these questions and you could maybe reply in an email and I could send them to some of the campers.
That'd be fun.
But I'd like to thank you for taking the time to call into our camps today, telling us a bit more about what you're doing with chemistry and answering all these great questions. So thank you very much.
Okay, thank you.